Bismillahirrahmanirrahim. Assalamualaikum and good day. So inshallah, we will begin our lecture on chapter 9 entitled as Vibration and Wave. So this is the overview of our chapter 9, where listed here is the subtopic and the page for your pre-reading, the examples as your syllabus, as well as the tutorial questions. So to begin this topic, let's recall about Hooke's law and force involved within the Hooke's law. Right? So the force acts towards the equilibrium position is called as restoring force. The restoring force always pushes or pulls the object towards the equilibrium positions. So the law involved is F, or spring force, is equivalent to the negative kx, where the x is the displacement. It could be compression or elongation of the spring, and the k is the stiffness or spring constant, or also known as force constant. The restoring force, the force within the spring, is directly proportional to the displacement but in opposite direction. That is the meaning of the negative sign here. Alright, so if we take a look on this diagram, where we have initially the block is pulled to the x position from its equilibrium position, or x equivalent to 0, reaching x equivalent to positive maximum displacement. And then after it is being released, okay, the Fs going to bring the block towards its equilibrium position. At this instant, the Fs becoming 0 because of the formula of Fs equivalent to negative kx. When you substitute the x value as 0, the Fs becomes 0. However, the block keeps on moving to the left because of the conservation of momentum. So whenever it reaches negative maximum displacement to the left, okay, for example, just now we displaced to the right 5 centimeter. So whenever it reaches negative 5 centimeter, okay, why is it the amount is the same? Because we have frictionless surface. So there is no friction involved, there is no energy loss, therefore the displacement to the left is also 5 centimeter maximum. And then the Fs going to be maximum again, but in opposite direction, therefore the Fs going to push or bring the block to the right. So this motion continues left right back and forth until the end of time. That is what Hooke's law talk about. Now we're going to take a look on the vibration. The vibration going to give us the meaning of the simple harmonic motion. Okay, what is simple harmonic motion? The motion that occurs when net force along the direction of motion obeys Hooke's law. The first information here. The force is proportional to the displacement and always directed towards equilibrium position. So this is actually the meaning or the story or the theory behind the Hooke's law. The motion of the spring mass system is an example of simple harmonic motion, the system that we are looking at just now. Not all periodic motion over the same path can be classified as simple harmonic motion. For example, the movement of the satellite orbiting the Earth, the movement of the moon orbiting the Earth, many other rocking chair, for example, many other type of periodic motion. Doesn't mean that whenever it is a periodic motion, confirm it is a kind of simple harmonic motion. So another information about simple harmonic motion, or SHM, that the force needs to obey Hooke's law. This is the most important part. Now, let's take a look on this. We have a vertical spring here attached to a block, okay, Okay, then the block is attached to sketch a graph on the motion paper. Graph paper is in motion here. So whenever the motion of the spring is up and down, we can have the visualization of the displacement of this object or block is up and down in terms of sinusoidal wave function. So that is how we know that vibration is actually also known as simple harmonic motion. Why is it simple harmonic? It's harmonic because the motion is up and down nicely. Simple because we consider no friction at all. Right? So 3 important things or characteristic or properties that very important in simple harmonic motion is amplitude, period, and frequency. Basically, amplitude is maximum displacement of our object from its equilibrium position. It could be positive, A, positive amplitude, if the displacement is toward positive direction. It could be negative of amplitude, representing the displacement towards the negative direction. For period, it's actually time taken to move for a complete vibration or revolution. Okay, that the time needed to complete one revolution known as period, right? And then for frequency is telling us about number of complete cycles or vibration over time or per unit time. It could be per second or hertz. It could be per minute. It could be per annum or year. Reciprocal of a period is also known as frequency. So if we want to translate the information of the frequency and period here, if we have a graph of displacement of our object versus time taken, so we can see here maximum displacement here is positive A. Maximum but in negative direction here is known as negative amplitude. And then the time taken to complete one vibration. So from this to this, okay, this is known as period. Okay, now we're going to take a look on the acceleration of an object in simple harmonic motion. So we know that the object for mass spring system just now moving from rest to certain movement, to certain speed, to certain velocity. Therefore, a sudden change of movement there going to give us information about acceleration. Based on Newton's second law, we have the relationship between the force axis Fs within the spring system equivalent to ma, but then now Fs also equivalent to negative kx. Therefore now we can have rearrangement of the equation to produce A as the title or unknown to be solved, which is equivalent to negative kx over m. So now, okay, we know that the k is a constant. The mass also a kind of constant. So the one that keep on changing is actually the x, the position of the object. Therefore, the A is depending on the x. So we can conclude that the acceleration is a function of position. It means that the A will be varied or changed according to the x or position. So in this case, the acceleration is not a constant value, is not a uniform value, is not an average. Okay, therefore the uniformly accelerated motion equation cannot be applied. The kinematics equation before cannot be used in this simple harmonic motion situation. Let's take a look on the example 13.1. Simple harmonic motion on a frictionless surface. A 0.35 kilogram object attached to a spring of force constant this amount, Newton per meter, is free to move on a frictionless horizontal surface as in figure. If the object is released from rest at x equivalent to 0.1 meter, find the force on it and its acceleration at x equivalent to 0.1 meter, 0.05 meter, 0, and also negative 0.05 meter, and also negative 0.1 meter. So we are going to apply Hooke's law, Fs equivalent to negative kx, and F will be maximum if the x is maximum. The maximum of Fx is the A. So we substitute the value of 0.1, we will see it has negative 13 Newton. Even though our x is positive maximum, our Fs is in negative direction. Maximum in terms of value, but in negative direction because they are in opposite direction. To have the A, Newton's second law, F equivalent to ma, and our F is the Fs. Okay, so we have here the A is negative 37.1 meter per second. If we are using F as the maximum value, the A that we calculated here also the maximum value. Okay, so take a look on this. At position of maximum positive amplitude or maximum x in positive direction or positive amplitude, okay, the force is maximum but then in negative direction. The A is maximum in terms of value but in negative direction. When we recalculate, alright, the A according to the position, the x and also the F, okay, we will see them, okay, they are in opposite direction. Alright, if this one is 0, everything is 0 because it's depending on the x, remember? And then whenever it has negative position or maximum displacement, so the F and the A will have positive sign. Alright, exercise 13.1 will be your homework. So now let's proceed to elastic potential energy. We know that the energy stored within a spring system is half kx squared. Alright, so we already derived this equation in terms of work done chapter previously. So the elastic potential energy within the spring can be added to the statement of conservation of work energy theorem. So this is a recall where this one begins with the E initial equivalent to E final. Okay, when we can have this condition, actually work energy theorem talking about WNC equivalent to delta E. Whenever the WNC is 0, the delta E will be equivalent to 0. That gives us the information of E final equivalent to E initial, or like this. Right? So energy in a mass spring system. So if we refer to this diagram, initially the block is not attached to the spring system. Now the block is moving toward the spring with V initial. In this situation, for the whole things here, the one that having energy is actually the block itself. Okay, by itself is half mv initial squared. Okay, now whenever the block going to compress the string, reaching the x to the right position, now both of them, it is not stopped yet. Okay, it having the V start to compress the spring. Now the energy is in terms of two things. Firstly, kinetic energy, because the block has the motion, half mv squared. And also the potential energy because the spring being compressed, which is half kx squared. Right. The E total here will be equivalent to this E initial. Right. Now, after the spring being compressed and reach its maximum displacement to the right, now the block going to stop a moment before it turn back. Okay, so at this instant, the V of the block becomes 0, stop a moment. So there is no more kinetic energy within the block. The whole energy is in terms of potential energy within the spring, which is half kx maximum squared. right? And now the force within the spring, the restoring force or spring force, going to push the block back to the left, okay, until it reach the initial point or the equilibrium point x equivalent to 0. And at this instant, the block going to move to the left, okay, where when we observe the whole system here, the E total is in terms of kinetic energy consists or within the block, which is half mv squared. Even though it has negative sign here, whenever you do the squared, the negative will be positive. Alright, so example 13.3. A 13,000 Newton car starts, this is the weight, okay, not mass only, the weight. Starts at rest and rolls down a hill from height of 10 meter. It then moves across level surface and collides with a light spring-loaded guardrail. Okay, here is the guardrail. A, neglecting any losses due to friction and ignoring the rotational kinetic energy of the wheel. Okay, find the maximum distance the spring is compressed. Assume a spring constant of 1.0 times 10 to the power of 6 Newton per meter. Calculate the magnitude of the car's maximum acceleration after contact with the spring, assuming no frictional losses, and see if the spring is compressed by 0.3 meter. Find the change in mechanical energy due to friction. Alright, so the first part, we neglecting any losses, so there is no friction, we consider that. Okay, we also consider no effect of rotational kinetic energy involved. And then now we need to calculate the maximum distance the spring is compressed, the amplitude. So by using conservation of energy, okay, mechanical energy can be used because there is no friction. So we have E initial, E total initial, okay, E total initial equivalent to E total final. So the kinetic energy initial 0 because the V is 0, half mv squared, right? Because it starts from rest. Okay? Because there is information given here. Starts at rest. Right? So now, okay, the potential energy of the car, yes, we do have because it has height. So mgh, right? The potential energy within the spring, not yet because there is no compression or elongation yet initially. And then kinetic energy of the system, okay, 0 whenever it's already compressed the spring to the maximum displacement is going to stop a moment. Therefore kinetic energy of the car 0, kinetic energy of the spring also 0. Okay, and then potential energy now becomes 0 because it's on the level already, there is no more height. Okay, so mgh becomes 0 because of there is no h anymore, right? And then PES, yes, we do have, must be half kx maximum square. So now our task is to solve the x maximum. So rearrange the equation. Now you have the x as the title, substitute all the values given. The x is 0.51 meter. Okay, part B, calculate the magnitude of the car's maximum acceleration after contact with the spring, assuming no frictional losses again. So we're going to use Fs equivalent to F, net force, which is Ma equivalent to negative Kx. So A equivalent to negative Kx over M. And our M, not directly given to us at the mg, right? So we have to use the mg. Whether you're going to do it beside this aside by itself to calculate the m firstly, or you can put it as like this straight away. The m here is mg, therefore the upper part of it also need to be multiplied with a g. So now we have this kind of equation. Substitute all the values given, you will see your A is negative 380 meter per second squared. If you want to refer only the magnitude, then we're going to do the modulus of that value, give us 380 meter per second squared. Now part C, Okay, so the compression of the guardrail is only 0.3 meter only. Okay, find the change in the mechanical energy due to the friction. So it's not reaching the maximum. It means that there is friction exists. So based on work energy theorem, WNC equivalent to delta KE. Delta E. Okay, or E final minus E initial. Okay, so now we are going to calculate the WNC, the work done due to the friction. So we have, okay, this is E final. Kinetic energy stop already, right? So the V final 0, therefore KE final 0. PEG, there is no more height. Okay, so PEG 0 because H is 0. PES final, yes, we do have compression, so half kx squared. This is the unknown. This is the information of 0.3 meter just now. KE initial, everything start from rest, therefore is 0, the V is 0. PEG, yes, we do have MGH. And the PES initial, no, we don't have any compression or elongation initially for the spring. So calculate, then you're going to have your WNC equivalent to negative 8.5 times 10 to the power 4 joules. Negative here means that we are losing the energy due to the frictions. So exercise 13.3, take it as your homework. Okay, let's take a look on the velocity as a function of position. So now we just observe the x, the a. Okay, now we're going to take a look on the V itself. So let's begin with this diagram. So what we have here, a mass spring system. Let's say we elongate. Okay, we displace the mass spring system. This one attached, okay, the block is attached to the spring, fixed to the spring. So we elongate from equilibrium position from x equivalent to 0. We displace or we elongate the mass spring system to the right, reaching positive amplitude. At this instant, it is not in motion yet. The V is 0. At this instant, the total energy is in terms of PES, which is half KA squared. And then whenever we remove our hand, the block going to move. Okay, so it has the V. Okay, and it has the X, which is not the A anymore. At this instant, it's not reaching the equilibrium position yet. Therefore, at this instant, the E total is in terms of potential energy in spring, half kx squared, plus the kinetic energy of the block, half mv squared. So we know that the energy must be conserved. Okay, must be conserved. Therefore, E total is equivalent to KE plus PES. Is the initial or origin of the equation given here. Only PES involved. There is no PEG because there is no elevation, there is no height, there is no delta y involved in this situation. So from this formula, why is it E total equivalent to half KA square? E total now, okay, equivalent to PES maximum. If this one maximum, this will be 0. If this becomes 0, the PE become maximum. Remember that? So E total, we can take it as maximum in terms of KE maximum or PE maximum. For this case, we are using the PES maximum as our E total. Alright, so now rearrange the equations. Okay, we see we have half everywhere. All items have half, so half can be cancelled out. Alright, and then now we have our aim is to solve for the V. Okay, so we're going to rearrange the equation. We will have this kind of equation. So the K is a constant, stiffness of the spring or spring force or force constant. The m is the mass of the block. Okay, the a is the maximum displacement or amplitude of the mass spring system. The x is the position that we want to consider. So, okay, the v here going to be varied according to the x. That is why this equation known as velocity as a function of position. Right, then the velocity, the unit of it is still meter per second. What does that mean by plus minus here? Okay, when you have the square root, you have to choose whether your final answer should be positive final answer or negative final answer. It depends on the direction of your v at that instant. Okay, it will depending on the direction of your system. Is it to the left? Is it to the right? Is it to the positive direction or is it to the negative direction? You yourself need to decide it and put the plus or minus symbol. Okay, so take a look on the statement here. Speed is maximum at x equivalent to 0. Why is it so? You see, when you substitute the x equivalent to 0, the whole formula here is a maximum value. Okay, that is how we know that whenever it reach equilibrium position, okay, the block going to attain its V max. This is the biggest V it can attain the moment it reach equilibrium position. Okay, the speed is 0 at x equivalent to positive A or negative A, because when you substitute positive A or negative A here, the product of this will be 0. So square root of 0 is nothing, it's 0. Therefore, we know that the V will be 0 at x equivalent to positive A or negative A. Okay. The positive negative indicates the object can traveling either in the direction. The value is the same, but the direction represented by positive or negative. Okay, example 13.4, a 0.5 kilogram object connected to light spring with a spring constant of 20 Newton per meter oscillate on a frictionless horizontal surface. Calculate the total energy of the system and maximum speed of the object if the amplitude of the motion is 3 centimeter. B, what is the velocity of the object when the displacement is 2 centimeter? So is now varied, change. Compute the kinetic energy and potential energy of the system when the displacement is 2 centimeter. So let's begin with the A. Calculate the total energy of the system and the maximum speed of the object if the amplitude given to us. So we know that the E total equivalent to kinetic energy plus PEG plus PES. Okay. Initially, there is no movement, so V confirm 0, therefore K is 0. PEG, there is no height, there is no delta Y or H, therefore PEG is 0. PES, yes, we do have in terms of maximum of it because half KX maximum squared or A squared. So this is the E total, which is in terms of PES maximum. Alright, and then for part B, what is the velocity of the object when the displacement is 2 centimeter? Either you want to derive it by using this equation or you straight away use the derived equation just now here. So can be done. So you see, substitute everything, you will get 0.19. So why is it K is 0? Initially no movement, no elevation, no height. PES, yes, we do have, this is a value of it. And then KE will be maximum whenever the x final is 0. And then PEG will be 0, no elevation, no height as well. PES will be 0 because the formula of PES is half kx square, isn't it? When the x is 0, the PES is 0. Okay. So bear in mind these two information. X initial is A and x final is 0. For example, PE is half PE, this is PES final, half KX final square. But your x final is 0. That is how we get PES final becomes 0. Okay. And then rearrange the equation. We want to solve for V max. We will get V max 0.19 meter per second. This one. Okay, part B. Compute the velocity of the object when the displacement is 2 centimeter. Now we're going to use this equation. You want to derive it all over again, also can, no problem. But then long way, isn't it? Why don't you straight away use the derived formula? So you substitute the x is 0.02. Bear in mind, everything must be in SI unit. Okay, because the unit for your K is Newton per meter. Right, then you will have plus minus. What does that mean by plus minus? Okay, depending on which side. 2 centimeter is too general. Is it on the left? Is it on the right? So you have to determine the sign of your V. Okay, compute the kinetic energy, kinetic and potential energy when the displacement is 2 centimeters. So again, we are going to repeat half mv squared for KE. But then you're going to substitute the V at 2 centimeter because the question asking for that. Then PES, the X is 2 centimeter, but careful, must be in SI units. Okay, exercise 13.4. Okay, homework. Alright, I'll continue this section within the second part of the video. Thank you.